All right, let's begin. Homework 7B, that's your last homework assignment. That'll be due a week from today on Thursday the 7th. We are going to get into Chapter 8 next week, but we'll do some activities in class and there won't be any actual homework assignments associated with Chapter 8. So this energy equation set of problems will be the last thing that you submit. Today we're going to continue talking about the energy equation, specifically a little bit more detail about how pipe friction works, and kind of give you an idea of where we're headed for those of you who are sticking around for hydraulic engineering next semester. We're also going to talk about grade lines, which are a way of visually representing where the energy is in a system. Any schedule questions before we move into the new material? All right. One of the factors that determines how much energy is lost as water flows through a pipeline is the roughness of the material that's used in the construction of that pipe. And this property, epsilon, sometimes in different texts it's denoted K sub S, it's called the equivalent sand roughness. And it's a way of expressing how rough a material is if it was represented by an equivalent sand diameter. And so some of these materials are going to have irregular surfaces to them, and so it's hard to measure, like on a microscopic level, the height of the little peaks and valleys of a material if you really zoom in on it. And so the way that's kind of been standardized of talking about the average size of those irregularities on a surface is if you were going to represent those irregularities as an equivalent roughness of sand. And so in the case of really smooth materials like glass or drawn tubing where it's copper or brass that could be extruded, then there's a very smooth surface there such that the equivalent sand roughness is far less than 1 millimeter in diameter. But then there are other materials like cast iron where, because of the crystalline structure of the material, the irregularities of the surface have a larger size, and so you can see here 0.26 would be kind of an average equivalent sand roughness for that type of material, all the way up to concrete. And I'm sure some of you have seen a brushed concrete surface before where maybe they're intentionally trying to make it a little bit more rough to provide traction if it's maybe a steep grade or a surface that could receive some snow and ice during the winter months. So a rough surface maybe would be high enough to have an equivalent roughness of 3 millimeters. Now the reason that we talk about these different roughness heights is that there is a laminar sublayer that will exist above, in most cases, the material surface. And we've talked about the no-slip condition and how water doesn't actually move with a velocity over a surface, but as you get closer and closer to the physical surface of a pipe, that the velocity of the water is decreasing until it reaches zero. And so you remember from Reynolds number that the Reynolds number is the velocity times diameter divided by kinematic viscosity, and a Reynolds number of less than 2,000 indicates laminar conditions, where more than 4,000 is turbulent conditions. And so one of the things that we sometimes do in analyzing how rough a material is going to be and how much energy is lost is looking at the thickness of the layer that is laminar versus the height of the material that may be sticking out and poking through that laminar sublayer. And so we'll go into a lot more detail about that later, but that gives you kind of a glimpse of why we're interested in talking about it. Now the interesting thing is that in the past people used whatever materials they could get to convey water. And this is a picture of a wooden pipe where these are sections of a board that very meticulously and labor intensively had to be fitted together, and then there would be a wire coil that went around the outside of this, and so it's similar to a barrel. And it was very skilled work to make a barrel and also skilled work to make wooden piping. Wooden piping, even if it was relatively smooth, would have a roughness that's greater than that of the new steel type pipes that we're using now. And so not only was it expensive and labor intensive, but there would be big head losses as the water went through that pipe. This is a really important figure that you'll probably see more in the future, and this is called a Moody diagram. And let me talk you through the relationship here. Now, first of all, the equation that's at the top, that's called the Darcy-Weisbach equation. And the Darcy-Weisbach equation tells you how much pipe loss there is due to, how much energy loss there is due to pipe friction. Remember that energy loss, H sub L, has two individual components. There's the local loss component of it, which we've talked about in lab, is due to fittings at a certain location. And then there's the distributed losses, which is related to flow through pipes. And this is just about the pipes. It's not about the local losses. So what this Darcy-Weisbach equation says is that the amount of energy loss due to pipe friction, which we're going to measure in units of length, that energy loss is a function of the F value, and F is just an energy loss or a friction coefficient, the length of the pipe. And so, for instance, a 100-meter length of pipe would have twice as much energy loss as a 50-meter length of pipe. So it's a linear relationship between length and energy loss. Now, the velocity term is squared, which means as the velocity, the average velocity through a pipe section increases, there's an even larger effect on the energy loss. So it's a nonlinear relationship for velocity. D is the diameter of the pipe, and then 2g, of course, that g is the gravitational constant. So all of these values, F, L, V, D, and G, are easily classified, but the F value, the friction factor that we should use to calculate how much energy loss there is due to pipe friction, F is pretty hard. F is not the same thing as the equivalent sand roughness, this epsilon. This is a physical constant that depends on the material, but F depends on several things, including this material roughness. And so the first thing that we do to find out what is the F value is go to the vertical axis on the right-hand side of this figure. And what it says here, relative roughness is the K sub S to D. So in other words, that's the ratio of the equivalent sand roughness of the material to the diameter of the pipe. Now remember, K sub S is just another variable that's commonly used in place of epsilon. So what you would do if you had a galvanized iron pipe that had a diameter of 150 millimeters. Can I use the marker? Can always count on you. Can't always count on myself, but fortunately I've got students who are prepared. Thank you. All right, so let's say that we have a pipe with a diameter of 150 millimeters. Okay, so here's our diameter, 150 millimeters. And then if we zoomed in on that pipe, you know, it's irregular, and the K sub S of that material is 0.15 millimeters because it is galvanized iron. Okay, so in order to find out what's the F value, the first thing that we'd do is we'd come up with the K sub S to D. And in this illustration that we're talking about, it's 0.15 millimeters is the average diameter of the material, and then the diameter of the pipe is 150 millimeters, and so then the ratio there is going to be 0.001, right? 0.001. And so what we'd do is we'd find this 0.001, and there's a solid black line there that starts to curve. Am I right, by the way, about that being 0.001? I don't have a calculator handy, and your brain works differently when you're standing in the front of a classroom and when you've got a calculator in your hand, but yeah, okay, 0.001. So this thick black line is the one that we would follow, but now we need to know what's the Reynolds number of the flow through the pipe. And so remember, the formula for Reynolds number is the velocity times the diameter of the pipe divided by the kinematic viscosity. So we know our diameter of the pipe is 150 millimeters, And kinematic viscosity, that's a fluid property that's a function of temperature. A typical value for kinematic viscosity would be 1 times 10 to the minus 6th meter squared per second at maybe a standard 20 degrees Celsius. Now, the velocity of flow, that's how quickly is the water moving through the pipe. Here's where it gets tricky. Let's say that we're talking about one tank connected to another tank. And there's some elevation difference, and that's the driving force. That's why water is going through that pipe, is because the water is going to go from the high elevation tank to the low elevation tank. How quickly is it going to do that? What will be the velocity? Well, it depends on the elevation difference. Remember, we said that if there's a big elevation difference, the water's going to move faster than if there's a low elevation difference. But it also depends on how rough the pipe is, like how much energy loss is there as the water is flowing through the pipe. So we're starting to have a chicken and the egg scenario here, because the F value determines how much energy loss there is, but how much energy loss there is depends on the velocity, but we don't know the velocity until we know how rough the pipe is. And so oftentimes using this figure is an iterative process where the first thing you have to do is you have to guess what the velocity is through the pipe. So we'd say, well, maybe it's going 2 meters per second. And so what you'd do is you'd calculate some Reynolds number based on a guess value of the velocity. And then once you finally have a Reynolds number, you could find whatever the Reynolds number is, and you'd intersect that curve that you had before, and then you'd go over sideways and find the F value. And so then once you have an F value that's based on an initial guess of the velocity, then you'd put it into the Darcy-Weisbach equation, calculate the estimated energy loss, and then you'd go through that process again with an improved guess of what the velocity might be. Yeah?
Could you install like a flow meter right there at the entrance of that pipe to get what your Q value is and then divide it by the diameter to get your...
Absolutely. You can do physical measurement of what the velocity actually is, but when we're going to be using this equation is before it's built. You know, it's in the planning stages where we're trying to do design. And so where we are going to be saying, well, what diameter of pipe is required to get a certain flow rate. And so it'll always be an iterative process, because what this Moody diagram is illustrating is that if the water is moving slowly, there's going to be a different roughness effect than if the water is moving quickly. This dashed line here is defining the different regions. One region that's called rough turbulent zone, and another one that's the transition zone. And what it essentially means is this curve is flat some of the time, meaning that in the flat zone of this curve, it doesn't matter what the Reynolds number is. The F value is going to be the same. This flat zone, where the curve is flat, it means that the Reynolds number only depends on the relative roughness. But beyond that dashed line, in the curved zone, the F value that you should use partly depends on the relative roughness, and it partly depends on the effects of the Reynolds number. And so it's in that curved part of the figure that then this whole issue becomes iterative, where you don't know exactly how rough the pipe is until you know how fast the water is moving, but you don't know how fast the water is moving because you need to know the roughness to be able to predict that. And so that's called an implicit equation or an iterative equation, where sometimes the unknown is on both sides of the equation and you have to guess one part of maybe what's happening, and then gradually you'll iterate and you'll converge on the correct solution through a series of guesses and improved guesses. And that'll be a big part of the processes that we learn in hydraulic engineering, is when there are too many unknowns, guessing one of them and then converging to the correct solution.
How do you know, like, guess is high or low when you get it?
You know if your guess is high or low. So what we would do is, if we initially guessed, let's say, remember in this example I said 2 meters per second. So with a guess value of the Reynolds number, we could come up with a friction factor, and then we would put it into this H sub f, and then we would use the H sub f in the energy equation. P1 divided by gamma plus Z1 plus V1 squared divided by 2G is equal to P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus H sub L. And so we'd put that estimation of head loss into the energy equation and then see like what is the actual velocity based on that initial guess. And if we guess too high, then we can make a correction next time around and come up with a new Reynolds number. And so we'll get a chance to see that convergence process. You'll get some practice with that. But I just wanted to point out that this Moody diagram is a graphical way of solving for the F value. There are also equations that exist, empirical equations where you can estimate it numerically rather than having to use the figure. The figure is the easiest way of doing it, but there are more accurate ways that you can also build into an Excel spreadsheet. If you're going to be iterating, then Excel is a nice way of automating the calculations so you don't have to do page after page of calculations when you're trying to get something to converge. Okay, so in the lab you got to measure the effects of the local losses, and this illustration of the streamlines is showing that, for example, when water flows around a bend, there will be a separation zone where there's some turbulence and flow that's not going in the bulk direction. So most of the flow is going, first of all, from left to right and then downward. But as the water comes around this bend, there will be a location where there's some swirling and eddies and vortices there that cause a reduction in the effective flow area. And so that's why there is an energy loss. Is essentially all of the flow has to be choked down through a smaller cross-section because part of this zone is having a little bit of turbulence that isn't available for bulk movement of the fluid. And so we could measure a decrease in the pressure through that fitting. The K value is experimentally determined by the pressure change divided by the effect of the velocity there. So that's just rearranging the equation that you had in your lab handout. Now, the way that you would apply a given K value to find the local losses is multiplying it by the velocity head. Now this summation is just saying that if you have a pipe network with lots of different fittings, you don't have to find the head loss of each one of them individually, but rather as long as each one of them has the same velocity, you just add up all of the K values between two locations and then multiply the sum of the K values by the velocity head. If you have a series of different pipe diameters, then you'd have to sort of group all of the K values together and only multiply the K values by the velocity head that they're experiencing. But just for simplicity's sake, you can add the K values together. So this is that same table that was on the backside of the lab handout I gave you that shows some typical K values. Actually, this I think was on the handout I gave you in class on Tuesday. So we've already talked about the difference between, for instance, a 90-degree miter bend and how if you have the vanes there, that can kind of help aid the transition as the water is flowing around a corner and really reduce the K value and the energy loss that's experienced compared to if there is a 90-degree bend that doesn't have the vanes. Now, one thing that we didn't talk about in a lot of detail was in the case of expansions, how the ratio of the diameters affects the K values. So now look at if you have the really extreme change in diameter. So if you have the ratio of D to D being 0.2, then what that means is that the D1 is only 20% of the diameter of the D2. So maybe that would be a 10 centimeter pipe discharging into a 50 centimeter pipe. that is the ratio that would give us 0.2. So in that case, the K value, the K sub E, the loss would be 0.3, compared to if the two diameters are closer together, then that ratio will be closer to 1. So 0.8 would mean that you've got a 4 centimeter pipe going into a 5 centimeter pipe, not that big of a transition. There's going to be less energy loss, and so the K value is smaller. If the change in diameter is less extreme, then the K value would be smaller. Now, these two different columns are illustrating the difference between if you have these side walls that are gradually allowing the transition to occur. A 20-degree angle, that's talking about how smooth that transition, and a 180-degree angle means that you literally just have one pipe immediately transitioning into another without any kind of gradual transition between the two. And so this is what a 180-degree transition would look like, is just literally the water that's coming from one pipe is going to have to try and set up flow patterns into the other. And the reason why there are losses is because of the turbulence and the rotational flow that occurs in those side pockets. And there's less of that in a more gradual transition like is illustrated here. This illustrates the zone of separation and expansion. And one way of estimating the head losses that occurs in an expansion is simply by having the difference in the velocity head. So find the difference in the velocity, square it, divided by 2g. In the table that I gave you in the lab, it was specifying both for an expansion and a contraction K values where you'd be using the smaller diameter as the velocity head that you use. And that's a question I got by email last night after the lab is, which velocity head do you use for the K value when you have a small diameter transitioning into a larger diameter? And it's the velocity head in the smaller diameter pipe in both of those cases. Okay, this next subject is what we're going to be spending the bulk of our remaining time in class today to discuss. And it's the idea of grade lines. This is a visual representation of where the energy is in a system. EGL stands for energy grade line. HGL stands for hydraulic grade line. And the difference between the two is that the EGL includes all three terms of the energy equation, whereas the HGL only includes the pressure head and the elevation head. And so EGL is going to be a graphical representation of the pressure head, the elevation head, and the velocity head at a certain spot, whereas the HGL, the hydraulic grade line, is just the first two, the pressure head and the elevation head. So in other words, what we can say is EGL is the HGL plus the velocity head. And so in this figure that's shown on the screen, the lower dashed line is the hydraulic grade line. And you'll notice that the energy grade line is above the hydraulic grade line. And the gap distance between the two is equal to the magnitude of the velocity head. And so here indicated is that alpha times V2 squared divided by 2g. And so the distance between them is a function of how fast the water is moving through that pipe. If you have a really high velocity, then there would be a big gap distance between the HGL and the EGL. Now here in the tank itself, they're showing that the EGL and the HGL are on top of each other. They're equal. So how does that make sense? Why is it that in the pipe there's a gap separating the EGL, HGL, but in the reservoir those two lines are coincident? Zero velocity, right. And so remember, we've said that for a very large diameter tank, even if water's flowing out of that tank and maybe the water level's going down ever so slightly, essentially the velocity there is negligible. And so EGL and HGL are equal because they have the same pressure head. There's no pressure at the surface. All of the energy is existing as elevation. And so there's only the Z term that has to be accounted for. And so the EGL and the HGL, where you have an open tank, it'll be the same line. Any questions so far? Okay, so starting at the left, all of the energy exists as elevation. Now, water is going to enter this pipe. And so energy starts to change spot on the left-hand side where before we've entered the pipe. Oh man, I'm so tempted to draw on the screen right now. Just imagine that I mean right there. In this spot, some of the energy exists as elevation, and some of it exists as pressure because there's a lot of water above it. Okay, so we've got energy as elevation, some as pressure. Now, when it's inside the pipe, it also has velocity head. So the water is moving once it's inside the pipe. So where did that energy come from? Pressure. You know, because the energy is in three spots. Once it's inside the pipe, there's still some elevation. You know, we're above the datum, so we've got Z. It's got velocity head, so it's moving now. So there's a slight reduction in pressure. And the reason why I mention it is to help explain this little line here, this segment of the line where the EGL and the HGL are diverging. And so for just a moment, the water level, excuse me, not the water level, but the EGL and the HGL are diverging, and so it's because the water is speeding up, it's gaining velocity, and therefore it's decreasing its pressure a little bit. And pressure is in the HGL term. All right, so now they're going down. That means energy is being lost. That's the interpretation of the fact that the EGL and the HGL is down. The rate of energy loss is because of pipe friction. And so if you have a lot of pipe friction, then you'll have a steep line. If you have very little pipe friction, then that EGL and HGL won't be as steep. But in this case, since it's a pipe that's discharging into the atmosphere, what that means is that when it does, the HGL will be equal to the height of the water. And I got to complain a little bit because this is a little sloppy. They should have had that HGL touch the water. As soon as the water comes out of the orifice is where that HGL should be in contact with the water surface. But the EGL is a little bit above it because even when it's moving outside of the pipeline, it still has velocity head. So I do it right now. Windows is in charge of my life. Yeah, that's a good idea. I'm sure they'd appreciate that. All right, so the EGL is above the water because the water's still moving. So it still has velocity head, but it doesn't have pressure anymore. All right. Okay, this little pipe that's coming off of the main branch here. Anybody know what this is called? Piezometer, right? A piezometer is where we puncture a hole and the water level rises to a certain elevation to indicate how much pressure there is inside of the pipe. And so you'll notice that the piezometer is rising to an elevation that's consistent with the HGL. So you can think in physical terms, the HGL is simply at every location, if you put in a piezometer, it's how high the water level would be at that point. And the EGL is where the water level would go if we had that piezometer actually facing the flow instead of flush with the pipe. And what's the difference there? What does it mean when it's actually pointing into the direction of the flow? Do you remember when we talked about?
Velocity has to be transferred into
Okay.
elevation head there.
Good. So he said the velocity of the water in the pipe, you know, there's some energy in the velocity. When the water intersects that stagnation location, all of the energy that was existing as velocity is transferred into a little extra pressure that pushes the water up higher. And so that's the actual physical representation of the EGL. It's the HGL plus all of the energy that exists as the velocity head as well on top of it. And so that's the idea, is that if we directed that opening into the flow, then we'd somehow capture the velocity head energy and turn it into a little bit more head inside of that tube. Okay, I think I've told you everything I can tell you about this figure. Any questions? We could, this is the picture of the EGL and HGL where it's a pipe that is discharging into the atmosphere. So on the whiteboard, I've got a drawing of two tanks that are connected together. And so let me show you what the EGL and the HGL would look like for this. First of all, the EGL and the HGL start at the water surface. And if it's going from one tank to another tank, then it's going to end where the HGL will end at the water surface. And so here I've got my little divergence thing here, and then it's going, and it's ending right at the water surface again. But the EGL is going to end above the water surface. So here's the EGL, and the HGL is below it. And this distance right there, that amount, like where the EGL is ending above the water surface, what that means is that when the water comes out of the pipe and enters the tank, it's suddenly losing its velocity head. All of the energy that was associated with the movement of the water through the pipe, that's a loss. And we talked about local losses. Remember in our last lab we were talking about K values and local losses, and so there's a little bit of a local loss at an entrance, and also there's a little bit of a local loss at an exit. So you lose the velocity head at the exit. And so that's why the EGL always ends a little bit above the water surface at a tank, but the HGL ends right at the water surface because, you know, we've got atmospheric pressure if it's air that's above that water surface, and so the EGL is above it. The HGL is ending right at the water surface because the HGL includes the elevation and the pressure. And so there isn't a big pressure change as the water goes from inside the pipe to the tank, but there is a big change in the EGL because of the losses. Okay, so here's what it looks like when you've got a pump. And pumps add energy to a system by adding pressure. A pump isn't necessarily going to change the elevation. I mean, in this sketch, it looks like the inflow pipe is a little bit above the outflow pipe. And a pump doesn't directly increase the velocity of the water. You know, if we have the same diameter coming in and going out, then the velocity in equals the velocity out. Continuity says it has to be that way. So that means that the only way a pump can add energy is by increasing the pressure. And so what this is showing is we've got the EGL on top, the HGL below. There's a sudden increase, and then it's gradually getting lower and lower again because there's the effect of pipe friction. And so in the direction of flow, both of these lines are getting lower and lower because of pipe friction, but then the pump suddenly has a vertical line that's increasing the energy in the amount of the pump head that's being added, and then the gradual decrease of both of those lines continues due to pipe friction once we get through the pump. Any questions about how a pump affects the hydraulic grade line and energy grade line? Here's what a turbine does. So we've got the HGL and the EGL at the open surface of a water reservoir, and they're gradually going down because of pipe friction, and then there's a sudden drop. And this sudden drop means that pressure is being extracted from the system. On the left side of the pump, there's a lot of pressure in the water there. But then this turbine is using the pressure in the water to spin the vanes of the turbine. They're extracting electricity, and then as the water is discharged from it, then there's a lot less pressure than there was before it. And so that head is given up to the turbine and converted into electricity. And then this has kind of an unusual thing that after the turbine, it's showing that the diameter of the pipe, they have it gradually increasing. I guess they'd do something like that if they didn't want to have like a big jet of water coming in. If they're maybe having a gradual increase, then that's reducing the velocity of the water, so it's causing less of a scour and disturbance in whatever body of water is receiving the flow. But what that means is if the gradual increase in diameter, that means that the pressure is gradually going to be decreasing. And so that's why here they've drawn that the hydraulic grade line and the energy grade line are gradually getting closer and closer together because the velocity head is getting smaller as the diameter of that conduit is increasing. Okay. A nozzle. Think about what a nozzle does. We have a large diameter pipe decreasing down to a smaller diameter, and what comes out of that is a jet of water with a higher velocity than it did prior to the contraction. And so here we have low velocity increasing to high velocity. And so the distance between the HGL and the EGL is getting bigger as the velocity head increases. So that's why there's a divergence between the two. And then you can notice that they've got the HGL terminating at the free surface of the water. So you have to have that line intersect the water itself when the water emerges from the orifice. But then the EGL is above it because this water still has velocity even after it comes out of the nozzle. Okay, I already showed you a little bit about two tanks. But in that first example I drew, it was the same diameter pipe. In this illustration, they're showing what happens if you have two different pipe diameters. You've got a large diameter pipe that's transitioning to a smaller diameter pipe. Now, flow in to the pipe network equals flow out through the pipe network. And so the Q in both of these pipes is the same, but the velocity is going to be much larger in the small diameter pipe because the cross-sectional area is less. So since it has a higher velocity, that means the rate of energy loss is going to be much greater. That's why the line is steeper. So if you're ever given a situation where you've got two different pipes like this and you're trying to sketch the energy grade line and the hydraulic grade line, you need to remember to make this, the smaller diameter pipe, both the HGL and the EGL are going to have steeper lines than the larger diameter pipe. Now, drawing this is a little bit of a, it's an art and like something you have to learn by experience. So the way that I usually would do it is start at the end, and you know it has to be kind of a steep line, and then you start at the other location where you know where the EGL and the HGL should be, and it should be not quite as steep. And so you have both of these lines beginning, and then you just kind of try and make them match up eventually. And so it would be easy. At first, you don't know how steep to make the line, and if you make it too steep, then you may not have enough vertical space left to make the smaller diameter pipe even steeper. So sometimes you'll have to do these in pencil rather than pen so that you can erase what you do and make a couple of adjustments so that finally it makes conceptual sense that you've got the bigger gap in the small diameter pipe between the two lines, since you've got more velocity head compared to the larger diameter pipe. Now what's happening here is actually pretty interesting, and what it illustrates is that it doesn't matter the physical location of the pipe, that the hydraulic grade line and the energy grade line are independent of the elevation of the pipe, because if the pipe is going up like this, the physical elevation of it, you're increasing the Z component. So the HGL you might think would be going up because the pipe is going up. But if you're raising the pipe's location, then you're going to be decreasing the pressure at the same time. And so The pipe itself, the physical location of the pipe does not affect the hydraulic or the energy grade line. But one thing to be aware of is that anytime the water is above the HGL, then you've got a negative pressure. And if this goes too far above the HGL, then you could have cavitation if the negative pressure there exceeds the distance from atmospheric down to the vapor pressure of the liquid. So here our greatest risk of cavitation would be here where you've got a big elevation difference where you've got the pipe high above the hydraulic grade line. Okay. So the key things that I'm going to be looking for when I grade your drawings, and I always include a problem like this on the final exam, because this is important stuff, and also because it's easy to grade. It's easy to grade a sketch. I'd be looking at whether you have divergence between the EGL and the HGL. I'd be looking at if you have the labels on them. The EGL is always above the HGL. Here the slopes are parallel. There isn't going to be any change in diameter, and so there's always going to be the same gap distance between the EGL and the HGL, and then making sure that the EGL terminates above the water surface. Those are the key things that I'd be looking for if I was grading one of your sketches for hydraulic and energy grade lines. The key thing with the pump is that instantaneous increase in energy. It shouldn't be slanted sideways. It's just a vertical line because it increases the pressure right at a location. Okay, I want you to get some practice drawing these, and this is always kind of funny. The first time you have to draw an energy grade line or a hydraulic grade line, it's hard to do because you don't know exactly how steep to make the line. So you can work with this either individually or with a classmate if you want to talk through it. It helps if you've got like a little ruler, or maybe you can use a credit card for the straight edge. So there's one question on the front and one on the back. And my suggestion is start with pencil. Draw the EGL and the HGL, including the labels for both. We'll take a look at the solution and we'll talk through it in just a moment. All right. Does yours look like this? Now, there's some wiggle room on some of these things, but let's talk through the required elements, and then I'll explain in certain locations where yours could conceivably, depending on interpretation, look a little bit different. So, what are the must-haves? Well, first of all, you must have a label that the EGL is on top and the HGL is the one that's on the bottom. Another must-have is that the slope should be shallower for the large diameter pipe as compared to the small diameter pipe. So that thin line compared to the thick line, that's meant to represent that this is a small pipe and that's a big pipe. And so what that means is the water's going to be moving fast through the small diameter pipe. It's going to be moving slow through the large diameter pipe. So this slope should be bigger than that slope. And then the other thing is look at the gap distance between them. So there should be a bigger gap distance because the velocity head, which separates the two, the velocity head is bigger when you have faster moving velocity because of the small diameter pipe. So big gap, small gap. Steeper, less steep. Do you have a question?
Yeah, doesn't the HGL actually increase when you have a larger diameter?
That's a good question. So he's asking about the pressure increasing because the diameter of the pipe is increasing, and it depends on how much energy loss there is at that expansion. It's conceivable that what you could draw is you could draw maybe the HGL matched up for the two, or maybe the HDL even goes up a little bit. So that's one of the points of ambiguity, is if there's enough energy loss at that transition, then the HDL could be below, equal to, or above. The HDL has that freedom, that the EGL definitely should be going down. Yeah?
How are those lines not touching? Like, how does, like, they don't really...
It just means that there's a loss there, an energy loss. So there's a sudden decrease in the amount of energy because of this fitting there. But you could make it so that they touch. You know, that's why I said that some of these things there's a little bit of wiggle room in how you draw it. Other things there's no wiggle room. And how the two connect, there are different ways that you could draw it that could be accurate. Yeah.
So the big black line determines how it jumps down?
Partly, yeah. So you're talking about at the exit there?
Yeah.
Okay. So if we had it flipped so that it was the thick line first and then the thin line, there would have been more velocity head, and the EGL would have been higher above that water surface. And so it would have, you know, the line is only a little bit. The HDL is just slightly above the water surface, but it would have been much higher above the water surface if we had the small diameter pipe discharging into it.
So how would it have been different if it was just the same size, like small pipe through the whole thing?
Through the whole thing? Was the small pipe through the whole thing, then the slope would have been constant. The gap distance between the two lines would have been constant, and then we would have had this much of a drop. So the HGL would be touching the water, and the EGL would be above it. It would be a straight line. Yep.
So does the path of the pipe determine anything?
No.
So you had to do like a loopy-loop if you wanted it?
Yeah.
The same?
That just gave me a great exam question. A loop-de-loop in the pipe. Yeah. Now let me qualify that though, because we can take that to an extreme. In a horizontal 1 meter, there would be more than 1 meter of pipe. And so actually, you know, it would be tough to represent it. Like, let's go back to this. This is less extreme. This is a good example because, I mean, it's showing that the elevation of the pipe does not affect the EGL and the HDL. But where I've drawn it so extreme here, you know, if you had a loop-de-loop, then you'd somehow have to show that, you know, you're losing more energy in that section because you simply have more pipe length. So, but the general principle is it doesn't matter. The physical elevation of the pipe does not affect the EGL or the HDL. Is there a question over here?
Yeah, so does the pipe length, like if you have a curve like that, there's no pipe length, is that what it says, steeper slope?
Yeah, yeah. Okay. So, on the back side we have another scenario. I show you the water flow. So that little symbol there, is that a pump or is it a turbine? It's a pump. All right, so remember how to represent pumps. Here's an illustration of what happens with a pump. It's a straight line. Sometimes people are tempted to make it like kind of angled, but it's a straight up and down line for a pump. It's adding energy just instantaneously at a single location. Wait, I think I need to get better examples because it doesn't look like these two lines are parallel. They're supposed to be. They are supposed to be parallel. Yeah, it's close, but it's still obvious that they're getting further apart, right? So I wouldn't take off points for that, but I'd sort of be like, do better, you know? I'll do better. All right, so we got the EGL and the HDL at the top, assuming that this tank is full of water. And so the two diverge. We've got the HDL coming down, the EGL. This is the smaller diameter pipe. So it's steep. There's the big gap between them. Suddenly both go up quickly because this is a pump that's adding energy. Now how high does that have to be? Well, it has to be high enough that you can have a downhill to get you to the tank. You can't have it just be part of the way and then the water isn't going to be going up to the tank. It has to be going down to the tank. So you have to make this line, this vertical line, high enough that then you can do the downhill and still reach the tank. But you want to make sure that it's not too high because we want this slope to be shallower since the pipe is larger. So steep slope, shallow slope, big gap, small gap. EGL ends above the tank, HGL ends at the tank. Those are the key ideas.
Is the reason you make the pressure negative for the pump?
No. There's no reason. You could also draw it so that, I mean, it was just a consequence of me wanting to show that that's really a steep slope because it's the small diameter one. But as long as it's steeper than the one coming out of the pump, it doesn't necessarily have to be below it. Other questions? Yes?
When we're doing this, we're saying that the pipe is below, right?
Yes. Yeah. In all these cases, we're assuming that the conduit's flowing full. Okay. We have 14 minutes until class is over. How many of you have, this is a silly question, how many of you have mobile phones with you today? I thought so. All right, so here's what we're going to do. I would like you to take some of the remaining time. Now, you can still leave early, but not this early. The course evaluations are open, and I'd be glad to have your feedback on the course. And you could have done it already, and I think there are maybe, I get the statistics of how many people have done the evaluations, not who, but I think so far 4 out of 46 students have done the evaluations. And so the way that you get there is mymu.marshall.edu and then go to the student link, and then it's on student resources, and then go to course eval. And in previous semesters it was possible to do it on a mobile device. You didn't need the full laptop to do it. I'm going to step into the hall so you don't feel overly pressured by my presence to give a positive evaluation. I want you to give an honest evaluation, and if you have feedback about the course or about the instruction, I'd be glad to have any of your suggestions. I'm always interested to know what you think of, for instance, the videos that are being posted and if those are useful or not. Is it working, Austin? Yeah. Okay, yeah, so you are able to get to it through your mobile phone. I'll be in the hall. And if you have any questions you want to ask about the material, you can ask me in the hall. But yeah, I'd be interested to know your feedback for the course. And the same thing goes for the labs, too. There's separate evaluations for 318 versus 319, which is the fluid mechanics lab. So